Okay, welcome back everyone. So last time we discussed a very powerful method to solve the Schrodinger equation. Okay, and so we said that if the potential V of x is constant in time, then solutions to the Schrodinger equation take the form that capital psi of x and t can be broken up into two parts. First part is a lowercase psi just of x, so this is only a spatial component, multiplied by a phi of t, and then this part is just a time-dependent component. Okay, so we split up capital psi of x and t into two parts, one just carrying the spatial terms and the other carrying the time-dependent. And this part, little psi of x, okay, the spatial part, satisfies the time-independent Schrodinger equation, minus h bar squared over 2m, times d squared little psi dx squared plus v times psi is equal to e times psi. And the time-dependent part, phi of t, we can just write as e to the minus I times e t over h bar. Okay, so we covered all of this last time, and then we made one additional claim. Okay, and this is kind of the beauty of splitting it up into a spatial part and a time-dependent part, which is that we can say that the Schrodinger equation here admits an entire family of solutions. Okay, so we have this family of solutions which are psi sub n of x, okay, and n labels, is an index that labels which solution we're in. And so we can say that this family of solutions psi sub n, each has an energy E sub n associated with the psi sub n, and then if we put it all together, our most general solution to our full Schrodinger equation, we can write as capital psi x and t as equal to a sum over this index number n of some coefficient c sub n times psi sub n of x times e to the minus I e sub n t over h bar. And so this is a result from last time. And it arises because we're able to really break this up into a spatial part and a time-dependent part. Okay, and the most general solution that we can arrive at can always be written as a sum over the psi sub n times e to the minus I e sub n t over h bar, weighted by the appropriate c sub n coefficient. Okay, so those c sub n's give you the weight of each stationary state. Right, now we can even be a little bit more specific than that. Okay, so I'm calling these c sub n coefficients some sort of like a weight term or a way that you know how to add up all of these different psi sub n's, but specifically we can say that the magnitude of c sub n squared is the probability of being in the nth state. Okay, and we're going to keep that in mind as we go forward for the rest of the lecture, and in fact for most of what we're going to be doing over the next few weeks. All right, so it's always going to be a very nice and convenient thing to write our full solution to the Schrodinger equation in terms of a sum over these c sub n's times these stationary states. And now we know how to interpret these c sub n's in the sense that the magnitude of these c sub n squares gives us the probability of being in the nth state. So that's all you need to know about when you are constructing these sorts of things. Okay. One question that might arise is, well, why c sub n squared, right? Why not just c sub n? You know, what's so special about c sub n squared being the probability of being in the nth state? Okay, and we can show why it has to be the c sub n squared if we think about normalization, right? So if we want to consider normalization of our wave function, then we demand that the integral of this full wave function, capital psi of x and t, the magnitude of that squared, integrated over all of x, needs to be equal to 1. And so what we can do is take our full expression for capital psi of x and t, substitute in this version of it, okay, and what this gives us is that the sum over n of the magnitude of c sub n squared times the integral of the magnitude of little psi sub n of x, magnitude squared, dx, is equal to 1. Okay, and if you're wondering what happened to this e to the minus I ent over h bar term, when we're taking magnitude squared, then it means that we get one term with an e to the minus I ent over h bar, and then we get a complex conjugate of that term, which is e to the plus I ent over h bar, and those cancel. Okay, so we're just left with this, and we've already shown that each of the stationary states, psi sub n, is already normalized, meaning that this integral is already 1 for every single possible stationary state. Okay, and so if this integral is always 1, then we're left with the conclusion then just that the sum over n of the magnitude of c sub n squared is equal to 1. Okay, and this is exactly the expected result if it's the c sub n squareds that correspond to the probabilities of being in the nth state. Okay, like any good probability, if you add up all of the possible states of the system, if you add up all of the possible probabilities of being in the nth state, then you need to get one. Okay, so this is a very well-behaved probability. So to give more of an example of this point, just to get you familiar with how these probabilities are working and how we might write down certain wave functions, I want to consider, or just let's say, that we have a wave function that has a 90% probability of being in the n equals 1 state and a 10% probability of n equals 2. So if I told you that much, we have 90% probability of n equals 1, 10% probability of n equals 2, and I want to just write down the wave function that we'd expect, we can always say that our wave function, capital psi of x and t, is a sum over n of c sub n, psi sub n, e to the minus I, e sub n t over h bar. Right? This is our most general expression. And if we specifically have these conditions, okay, we know that only the first and the second n's contribute to this sum. So this would be c1 times little psi 1, e to the minus I, e1 t over h bar, plus c2, psi 2, e to the minus I, e2 t over h bar. And if we're in a 90% probability of n equals 1, that means that c1 squared is equal to 0.9. And so the value of the coefficient c1 is square root of 0.90. Psi 1, e to the minus I, e1t over h bar. And then that leaves plus square root of 0.10 psi 2, e to the minus I, e2 t over h bar. Okay, so knowing only the probabilities of being in each of these n states, we can construct the entire wave function. Okay, we get our coefficients right, and then depending on the exact form of the Schrodinger equation, we'll get to that in a minute, that will exactly allow us to determine what these wave functions, psi 1 and psi 2 are, as well as the energies E1 and E2. Okay? And what will turn out to be the case, and what we will find as we go deeper and deeper onto the course is that the exact forms of these wave functions will depend exactly on the Schrodinger equation that you're given and the potential in which the particle moves. Okay? And that's about where we're going to be going here for the rest of the lecture, and indeed for the next few weeks, is to really take some of these abstract ideas and start applying them to specific problems. Okay? And these types of problems that we're about to embark in are often called a particle in a box kind of problem, and in a sense, they're a rite of passage, I'd say, for a lot of physics students. Okay, but after just a couple of weeks of quantum mechanics, right? So this is week 3 of quantum mechanics. You'll already be starting to do problems that are directly applicable to cutting edge research. All right, and let me show you what I mean by that. So I'm going to try and show a few slides here. Okay, so what we're looking at here is a picture of an individual trapped ion in my lab. Okay, so this is a quantum particle. We use laser light to cool it all the way down so that it's very, very cold. And very well localized in space. And the way that we hold on to this particle is by applying electric fields to essentially trap it. Okay, and so in some sense, this is a particle in a box, right? This is a single quantum particle, right? It's an individual atom that we have confined to a little box, and that box specifically is made out of electric fields, all right? So it can't escape the box. Here's another example, and this is sort of similar to the type of work that our new faculty member in the physics department, Brian DeSalvo, does. So this is working with neutral atoms rather than charged atoms like I use. Okay, and here the box specifically is made out of laser beams, okay, that provide a confining force to the atoms. So again, we have quantum particles, and here the box is made up of laser light, and you can kind of see from these images on the right, this is the shape of the box. So the box can be made a cylinder, it can be made an actual square, it can be made as kind of 2 rectangles, or if you like, this is a square box with a big repulsive barrier in the middle. So there are a lot of different options of considering what a quantum particle in a box is, but this is used all of the time in modern research. Okay, so the main point that I want to get across here is that it is of fundamental importance in quantum mechanics to think about what happens when you have an individual particle and then you put it into some potential that traps that particle, right? And that's really where we're going for the next couple of lectures. And so our goal here will be first to determine exactly what shape box we are trapping our particle in. And then once we know that, to solve the Schrodinger equation for that shape of the box. Okay, and then by solving the Schrodinger equation, we can determine the wave function of the particle, okay, all of the allowed energies of the particle, and once we have that, we have everything. Okay, because the wave function provides access to any observable you can be interested in. The average value of the position, the momentum, the energy, everything that you care about is all going to be embedded in the wave function. So our goal is to find that wave function by solving the Schrodinger equation. So in fact, what we're about to do here is the key to all of chapter 2. It's the key to all of these particle in a box kinds of problems. So we are going to go slowly through it. We're going to consider an example that we'll introduce today, and then next time continue with the same example, right? We're going to go slowly to make sure that you really get a good feeling for these kinds of problems. And so the simplest possible problem that we can start with is often called the infinite square well. Right, and so the potential, okay, the shape of the box, if you prefer, is given by V of x is equal to 0 when 0 is less than or equal to x, which is less than or equal to a. And the potential is infinite otherwise. If I were to draw this shape, okay, this is V of x as a function of x. At x equals 0 and to the left, the potential is infinite. When x is equal to a and to the right, the potential is infinite. And then the potential is 0 between x equals 0 and x equals a. Okay, so what we're really saying is that the particle is trapped inside of this box and it's confined. The particle is confined somewhere inside. Right. So now, having met the Heisenberg uncertainty principle, we know it's a little bit of a nonsensical question to ask where exactly inside it is. We know that there's going to be some sort of a wave function that describes a probability of finding it in different positions inside. And we know that there's going to be some uncertainty associated with the exact position. Okay, but we can say that the particle is somewhere inside of this box. And our goal is to find the wave function solutions, given this potential, to help us understand better what things like the expectation value of the position can be, or what the probability of finding it, let's say, between x equals a over 2 and a on the right half of the box would be, or anything else that we could be interested in. All right, so our goal is to find the wave function here. And I'd like to split this up into two regions, okay, because in a sense, our potential has two different regions of interest. Okay, and I'll start with the simple one, right? So if we are interested in the wave function outside the well, okay, and by that I mean either x is less than 0 or x is greater than a. Okay, in some sense our answer is straightforward. We can more or less just write it down. Outside the well, we can say identically that psi of x and t is equal to 0. Right? We have an infinite potential barrier to the left here and to the right of A. Okay, and when we have an infinite potential barrier, the particle can't access these regions. This is exactly what we mean by saying that the particle is confined between 0 and A. Right? The particle cannot be outside of that range, which means outside of that range, the wave function is identically 0. Okay, and kind of the corollary to that is that also outside, the magnitude of psi of x and t squared is also equal to 0. And so this is another way of saying that there is no probability for our particle to be outside. Okay. So that's the easy case, right? Now, of course, all of the interesting stuff happens inside of the well, and so that's where we're going now. Okay, so inside the well, as a good starting point, just like we saw in the last lecture, we know that we can write capital psi of x and t as a spatial part, little psi of x, times a time-dependent part, phi of t. Okay, so we know that much. We also know that little psi of x obeys the time-independent Schrodinger equation, okay, where v of x is equal to 0 inside of our box. Okay, we're interested in this region inside right now, and inside we know exactly that v of x is equal to 0. Okay, so our time-independent Schrodinger equation we can write as minus h bar squared over 2m times d squared psi dx squared as equal to e times psi. Okay, this is our time-independent Schrodinger equation where I've set v of x equal to 0. I'm going to rearrange this slightly. Okay, I'm going to bring the 2m over h bar squared with a minus sign over to the right-hand side and write that d squared psi dx squared is equal to minus 2me over h bar squared I'm going to make that equal to minus k squared times psi, where I've defined this new number k as equal to the square root of 2me divided by h bar. All right, so all I've done in this last step here is to replace all of this stuff with the number k squared, where k is just this. Okay, so I've done only math here, and I think you'll see why in just a second. Okay. The reason to write it this way is because this way evokes something that is a very, very common problem in differential equation solving. Okay, actually, if you look at this in another context, just for a minute, I'd like to claim that you have seen this differential equation before. Okay, that the second spatial derivative of some function is equal to minus k squared times that function back again. Okay, this is exactly the differential equation that describes a simple harmonic oscillator. Okay, so springs and electromagnetic fields, anything that oscillates periodically in time, like a sine or a cosine, obeys this differential equation. All right, and so in fact, we can say immediately, having written it in this form, that our wave function solution, okay, this differential equation is solved by the functional form little psi of x is equal to a constant a times sine of kx plus a constant b times cosine of kx. Right? This is the general simple harmonic oscillator equation, and this is the functional form that solves it. Okay, if we wanted to really check this, what we would do is to take d squared psi dx squared, okay, take the second derivative of this function that's supposed to solve our Schrodinger equation, right? If I take the second derivative of this, second derivative of sine gives me minus sine back again times two factors of that constant k. So this is minus k squared times a sine of kx. And exactly the same thing for cosine. Second derivative of cosine gives us minus cosine. And again, we have two factors of k out front. So this is minus k squared times b cosine of kx. Okay, and this is exactly minus k squared times our original function a sine kx plus b cosine of kx, which is just the function psi. So exactly like our Schrodinger equation, we end up with the result that d squared psi dx squared is equal to minus k squared psi. Okay, so this is indeed the correct solution. So now what remains to be determined here is the constants a and b in our solution. Okay, and the way that we're going to determine those constants is based on the boundary conditions of the problem that's given to us in this infinite square law. Okay, so in general, these boundary conditions are going to be the things that govern what the allowed solutions are to our problem. And I'd say that there's a very important and general condition in quantum mechanics that we're going to lean on heavily here. Okay, and so there is one important, let me say, general condition in quantum mechanics. Okay, and this is that our wave function, psi of x, is continuous. Okay, it doesn't seem like such a, such an unreasonable condition. Okay, and in fact, if you think about electromagnetic waves or ocean waves or any other kind of wave that you're used to, it's pretty rare to think about one that is discontinuous. Okay, and things are really no different in quantum mechanics. And in fact, on your problem set this week, you're going to have a short problem that explores what happens if psi of x is not continuous, and you'll find that you end up breaking the universe and you get an infinite amount of energy and really bad things happen. Okay, so we're going to go with this general condition that psi of x is continuous. And the reason that this is such an important point is because it immediately allows us to place conditions on the allowed wave function solutions. Okay. So for instance, we know that outside of our boundaries, outside of our infinite square will, capital psi of x and t is equal to 0. All right. And so if the spatial part of our wave function, psi of x, is continuous, then these two conditions together demand that little psi of 0 is equal to little psi of a, and they're both equal to 0. All right? So in other words, right at the boundaries of the infinite square well, we know that the wave functions have to be equal to 0. If they weren't equal to 0, then there would be no way to make this wave function continuous with the wave function that's just outside of the boundary. Okay? So we know that at psi at x equals 0 and at x equals a, our wave function has to be equal to 0. Okay. So with that in mind, we can compare to our differential equation solution and see what constraints that places. All right. So for instance, if we check the x equals 0 point first, okay, so for x equals 0, we can say that psi of 0 is equal to a times sine of 0 plus b times the cosine of 0. Sine of 0 is equal to 0, so that drops out. Cosine of 0 is equal to 1. And so we have that psi of 0 is equal to b. And from our condition right here, that psi of 0 is equal to 0, we conclude that b must be 0. All right, so if this constant capital B were not equal to 0, then it would be impossible for this wave function to satisfy this constraint. It would not be continuous at the boundary. Okay, so what we know so far is that psi of x is equal to some constant a times the sine of kx. All right, so we used one of the boundary conditions and we eliminated one of these unknown constants. All right, so we determined what happened there. Okay, so now we have one additional boundary condition that we can still impose here, which is that the wave function evaluated at x equals a also has to equal 0. So what we require is that psi of a, which is equal to a sine of k times little a, has to equal 0. Okay. So I'll point out that, of course, we can also make capital A equal to 0 here, in which case our wave function is 0 everywhere, inside and outside. And technically, that is a solution to the Schrodinger equation. Okay, if you take the second derivative of 0, then that's equal to the energy times 0, and 0 is equal to 0. And that's allowed, but we often call it the trivial solution. Okay, so this is no real wave function, no probability, no particle even. Okay, but the Schrodinger equation accepts no particles and nothing going on in the universe as a valid solution to it. But we're interested in the more interesting one here. Okay. So assuming that capital A is not equal to 0, then this relation here can only be satisfied if we set the argument of this sign that Ka is equal to n times pi, where n is an integer, like 1, 2, 3, and so on. Okay, I'll point out that if n equals 0, then we would again have one of those trivial solutions to the Schrodinger equation. Okay, But if n is equal to 1 or 2 or 3 or really any integer, okay, if ka is equal to pi or 2 pi or 3 pi, and then sine of pi or 2 pi or 3 pi, etc., is equal to 0, okay, only at those specific locations. And so if this is true, then what it really implies is that this k, right, it can't take on any arbitrary value, but it has to take on very discrete, specific values that are indexed by a number n, and we say that k sub n, by this equation, is equal to n pi over a. All right, and that's kind of a remarkable statement. Right? What we're saying here is that this value of k, which remember can trace back to the energy that this particle can have inside of the well, right? So I'll remind you or ask you to recall that k is square root of 2 times m times e over h bar. Okay, and what we've just derived here, which is that to satisfy the boundary conditions and to satisfy the Schrodinger equation, k is not allowed to be just anything. It has to be some integer multiple of pi over a. And if that's true, then it means that energy can't just be anything, right? Energy also has to take on some certain integer allowed discrete values. All right, and so if we kind of follow up that thought, right, if k sub n is a discrete set of numbers, and we say that k sub n is equal to square root of 2 times m times a discrete set of allowed energies, E sub n, over h bar, we can rearrange this to say that E sub n is equal to h bar squared, k sub n squared, over 2m. And using our definition for k sub n, this is equal to h bar squared, n squared, pi squared, over 2 times m times a squared. Okay, so now this is really starting to feel like quantum mechanics, right? So all of a sudden, all we've done is start with the Schrodinger equation, we put a particle in a box, and what pops out of it is that the energies of that particle have to take on these discrete values, okay? This argument of the sine of k times a, or in our allowed wave function, sine of k times x, that k can't be anything, that k has to take on discrete values, and if there ever was a signature of quantum mechanics, it's that things like energy and other observables take on these kind of discrete values. They can't be just anything, they're indexed by some number, and we can calculate what specific energies are allowed here. All right, it's really like magic. All we've done is start with this infinite square well, solve the Schrodinger equation, and all of this discreteness kind of is forced upon us, and it pops out of the equations. All right, so we're almost done, okay, but I want to remind you of where we are so far. Okay, so far, we have that the solutions to our Schrodinger equation, I'm going to write them as psi sub n of x is equal to some constant a times the sine of k sub n x. Okay, and in this notation, this little n is an index for our nth allowed state. Okay. If we come back here and we pick the integer n equals 3, then we have a specific k sub n. We have a specific energy that corresponds to n equals 3. And I'm going to call this wave function solution psi 3 is equal to some constant times the sine of k3 times x. Okay, so everything is indexed by n here. Right, so the final thing left to do is to figure out what this unknown constant capital A is, and we can figure it out because we still need to normalize our wave function. Okay, it's 0 outside of the well, which means that if we integrate the magnitude of psi squared inside of the well, then we better get 1 because the particle has to be somewhere. Okay. So to normalize, we do the usual thing. We're going to integrate here over the region of interest. Normally it would be all space, but we know that outside of 0 to a, the integral has to give 0. So we're only going to integrate between 0 and a. Magnitude of psi sub n of x squared dx. This is equal to the integral from 0 to a of capital A squared times sine squared of k sub nx dx. And for normalization, that integral needs to be equal to 1. Right, the neat trick here is that the integral from 0 to a of sine squared of knx is equal to little a over 2 for any value of n. Okay, it's actually a neat mathematical identity. If you don't believe it, you could, of course, always just substitute in all of the different values of integer n. Okay, so you can try all of these different values of k. You can do this integral by hand, by Mathematica, by whatever, and you'll find that this integral is always little a over 2. Okay, so we have all of the pieces, and so putting it together, we have that capital A squared times little a over 2 is equal to 1. And this tells us that capital A has to equal square root of 2 over little a. And that's it. At this point, there are no remaining unknown things in our expression. Okay, we had a differential equation that we arrived at by starting with the time-independent Schrodinger equation and taking the potential equal to 0. And we have found that altogether, our Schrodinger equation for this potential is solved by a family of wave functions. Psi sub n of x is equal to square root of 2 over a times the sine of k sub n x. Okay, and that's equal to square root of 2 over a times the sine of n pi x over a. So those are our wave function solutions for an infinite square well. And each of these solutions has a corresponding energy. E sub n is equal to n squared times pi squared h bar squared over 2ma squared. Okay, and jointly together, these solve the equation that minus h bar squared over 2m times d squared psi sub n dx squared is equal to E sub n psi sub n. Okay, this is the Schrodinger equation that we started with. All right. If we were to look at these solutions a little bit more closely, we find that the allowed solutions are all higher and higher orders of sine waves. So if I were to write down in our infinite well, what is psi 1 of x? When n equals 1, we have square root of 2 over a times sine of pi x over a. Okay, and sine of pi x over a between 0 and a is really just like the first bump in a sine wave. Right, if I draw the psi 2 solution, okay, psi 2 gives us a full sine wave between 0 and a. Right, so this is sine of 2 pi x over a. And then I'll draw one more. Okay, psi 3 as a function of x. This one gives us essentially 3 pieces, a bump, a valley, and then one more bump. Okay, so you can really see what's going on here is that as we increase n, we get more and more and more wiggles in our sine wave. Okay, and this makes a complete set of higher and higher and higher orders of sine waves. So normally, people will call this one the ground state, which is another way of saying that this is the state with the lowest energy. And then these, and for all other n not equal to 1 states, these are all called the excited states. All right, so we have the time-independent Schrodinger equation, and we solved it to give this family of wave function solutions. That family of wave function solutions comes with these energies. The solutions themselves, at least the spatial part, look like these higher and higher orders of sine waves. And then as the very final thing to wrap it all up, we can put it together with the time-dependent part and solve for our full wave function solutions. Okay, so our full capital psi of x and t for our infinite square well can always be written in a form of capital psi sub n of x and t is square root of 2 over a sine of n pi x over a, and then a time-dependent part, which is e to the minus I times n squared pi squared h bar squared over 2m a squared times time. Okay, and that wraps it up for today. So next time, we're going to make some observations about the types of states that we've calculated, and then study some of their properties, and then work through a couple of examples for what happens when we start off a particle in a particular state or in a particular way inside of this infinite square well, and how we can use these solutions to calculate what goes on afterwards. Okay, so if you like this video, please subscribe, and I will see you in the next lecture.